Hello, I'm Andy Liu. I'm presenting to you from California, and my mentor is Matthew Levine. I'm presenting my findings on optimizing small sparse autoencoders. An autoencoder is a form of neural network that encodes, compresses, and decodes some amount of data. This is especially useful for images, um, which take up a large amount of space when uncompressed. For example, we may have our original image, we put it through an encoding function to give us a small array of numbers, which we will then decode into a reconstruction. For my first experiment, I tested applying different activation functions in the encoder and decoder functions in order to see which had the best reconstruction quality. I tested the sigmoid, tanh, ReLU, leaky ReLU, and JLU functions. From our results, we can see that all functions except the sigmoid performed decently well in reconstruction accuracy, while sigmoid had significantly more reconstruction error than the other functions. However, ReLU did take a long amount of time to train, which is less of a problem in actual applications, but in research, it's preferable to have lower training time. Next, let's talk about the next metric to introduce to our autoencoder evaluation, which is sparsity. The goal of an autoencoder is to compress our data into a smaller form, which means that the amount of space our encoding takes up should be measured when we are training autoencoders. Because we can't actually modify the number of neurons here, we can instead use unactivated neurons. For example, let's say we had this encoding of these images. Because two of our neurons are equal to 0, we know that they hold very little, if any, information about our encoding. That means we can effectively consider them eliminated, which means that we are saving extra space here, which is called sparsity. In order to encourage this, first I tried L1 regularization, where you add a penalty in the training based on how large the values in the middle neurons are. Here are the results. As you can see, after a certain point in the weight of our regularization, we start seeing some sparsity, as indicated by figure D, the non-zero activations. However, we also see a massive increase in our reconstruction loss. To put this into context, here's a chart of the visual accuracies. Without regularization, our original model had an MSE value of around 0.008, while the sigmoid had around 0.02 or 0.03. As you can see, with high regularization, we achieve MSE value. Our loss goes up to 0.07, at which point the digits themselves are indistinguishable. The reason for this is because most of our neurons values are being pushed all the way down to 0 and encoding almost no data. So the model is outputting a single identical image for every input. The way we fix this is by applying a threshold. Below a certain value, we cut off that value of the neuron and set it to 0 and don't count it in our evaluation. What this does is it forces the model to store values in significantly high values so that our mean doesn't continually drop to lower and lower magnitudes. When we apply this threshold, we can see much more reasonable results. As we increase the weight of our regularization with a threshold, we can see that through the number of non-zero activations in figure D, that we are actually achieving a much, much smaller of activated neurons in the middle, and maintaining a low mean value. However, this does mean that our reconstruction quality slowly lessens as the error grows, as seen in figure A. So for some final remarks, in this study, we found um, the magnitude of the effect different training functions can have on sparse autoencoders. They can increase or decrease the error in training time by several times. And we also found that um, plain L1 regularization was not as effective in training our sparse autoencoders, and that we needed to apply a threshold. Finally, we found that when choosing to apply regularization with a threshold, there is some compromise you have to pick between reconstruction accuracy, as shown in figure A, and our sparsification or compression efficiency. Thank you.